So today we will have 5 talks, including myself. So our next speaker is Dr. Clara Chew, and she will be talking about a primer on the soil moisture and the GNSSR.
Hey everyone, my name is Clara, and today I'm going to be talking about how we can use spaceborne GNSSR data to retrieve near-surface soil moisture. I'm going to assume that the previous talks y'all have seen have covered what GNSSR is generally, so I'm going to skip over most of that for now. But something I don't want to skip is describing a little bit of the history and motivation for why we want to use GNSSR to retrieve surface soil moisture. One little caveat to this talk is that I often use the terms GNSS and GPS interchangeably, even though they obviously aren't quite the same thing. So how did we start down this path? The earliest explorations of GNSSR data were for ocean applications, either sensing ocean surface roughness, which is related to wind speed, or trying to use the data for sea surface altimetry. One of the earliest inklings of what spaceborne GNSSR data would look like over land came way back in 2005, when a British satellite called the UK-DMC recorded a handful of reflections over land. There weren't enough observations to say anything definitive, and for the next 10 years, any observations of GNSSR data over the land surface were limited to experiments either on towers, balloons, or airplanes. In 2014, Surrey Satellite Technologies launched the TechDemoSat-1, or TDS-1 satellite. TDS carried a bunch of different instruments, but one of these instruments was a GNSSR receiver, which was kind of a test version of the receiver that was going to be flown on the Cygnus satellites. Although most of the people looking at TDS data were interested in what the data looked like over the ocean, there were a handful of people who were interested in looking at the data over land. And what we saw was pretty cool. We saw big variations in the reflected GPS signal as the satellite passed over rivers, and we also saw what we thought might be a sensitivity to soil moisture. But you know, we still weren't really sure. TDS was just one satellite, and it was only collecting GNSSR observations 1 out of every 8 days. So although this was so much more GNSSR data than we had had previously, it still wasn't quite enough. But once Cygnus was launched 2 years later, this field exploded. We were finally getting continuous GNSSR observations all the time, and what we saw was really cool. We were making plot after plot of how the Cygnus data changed over time, and time after time, we were seeing that the Cygnus data were responding to changes in surface soil moisture. Since we made those initial plots, there have been several successful projects that have shown that indeed Cygnus can be used to retrieve soil moisture. Later on in this talk, I'm going to tell you guys about some of these projects. So this is kind of what has happened going back from the mid-2000s to today, but I haven't told you guys why it happened. I'm not going to assume that most of you guys are particularly familiar with soil moisture or even happen to care that much about it. So now I think would be a good time to enter into a conversation kind of explaining the motivating factors for why we're doing the research that we're doing. So what is soil moisture anyway? Why do we care about measuring it, and how do we usually measure it? These are all questions that are usually answered within the first 2 sentences of the introduction to every journal article ever written about soil moisture. But today, let's take a little longer to learn about it. Now this might be obvious to a lot of you, but sometimes soil is dry, and sometimes soil is wet. A hydrologist might call a really wet soil saturated, but you can just call it for what it is: mud. Soil moisture is just the amount of water that's in the dirt. When we look closely at soil, we can see that it's made up of a bunch of different components. You have the actual soil grains themselves, which can be a combination of sand, silt, or clay particles, and then in between the soil grains, you actually have pore space. And the pore space can be full of either air or water. Hydrologists often define soil moisture as the volume of water for a given volume of soil, and they call that the volumetric soil moisture. Let's think about that for a second. So here we have a given volume of soil. I really wanted to do this outside today, but it appears that every single one of my neighbors is mowing their lawn, and it's really loud. So we take this soil, and then let's pretend that we're slowly adding water to this soil. As we add water to the soil moisture increases. But where does the water go? Well, it's actually going in between those pore spaces that I was talking about earlier. Once the pore space has been completely filled with water, there's nowhere else for the water to go, and the soil has reached its saturation. This means that the maximum value of soil moisture is equal to the amount of pore space in the soil, also known as the soil's porosity. The porosity of a soil depends on the relative amounts of sand, silt, and clay within the soil. For typical, normal, everyday, boring soils, the soil's porosity tends to vary anywhere between 35 and 45%, and this means that the maximum soil moisture value for a typical soil is also around 35 to 45%. What about on the other end of the spectrum? If I dried this baby out, could we get to zero soil moisture? Actually, no. At least not under normal earthly temperatures. There's always going to be at least a little bit of water that's clinging to the soil grains in this thin film. What all this means is that soil moisture is always going to be at least a little greater than zero. And for typical soils, this value might be between 2.5% to even 7%. And hydrologists call this the residual soil moisture content. Now let's go back to talking about this column of soil. Is soil moisture the same everywhere within this column? Also no. Let's pretend that it starts raining on this soil. The soil moisture at the top is going to increase relatively quickly, but the rest of the soil isn't going to experience that increase in soil moisture because it takes a certain amount of time for the water to infiltrate down. Conversely, if we start drying this soil, the soil layer at the top is going to dry out more quickly than the soil underneath it. So if we flip back and forth between raining and drying, it's pretty easy to see that the soil at that top layer is going to respond more quickly than the soil deeper underground. The deeper soil layer is often called the root zone because this tends to be the layer where plant roots take their moisture from. Not all plant roots, of course, but the most tasty ones. The root zone is generally defined as the soil down to 1 meter in depth. And the surface soil is just called the surface soil, and it's generally defined as the soil down to 5 to 10 centimeters in depth. Obviously, both the surface soil layer and the root zone are both connected, and they're both important. So why is soil moisture important to know? Well, do you eat food? Then soil moisture impacts your life. We couldn't grow plants without soil moisture, and plants need water to live. But not too much water either. This plant got too much water, and now it's dead. Quantifying changes in soil moisture over time is also one of the ways that we quantify and monitor drought. It's also important to know because soil moisture affects where and when places might get flooded when there's too much rainfall. If you think about it, the soil is actually the boundary layer between the ground and the atmosphere, and the moisture in the soil is constantly being exchanged between the ground and the air above it. In some regions of the world, an increase in soil moisture actually then leads to an increased chance of precipitation, and vice versa. So if you want a good weather forecast, you might want to know what your soil moisture is. Alright, so now we know what soil moisture is, and we know why it's important. But how do we usually measure it? There's only one truly direct way to actually measure soil moisture, and that's called gravimetric sampling. With gravimetric sampling, you're going to physically go out into the field or wherever you're interested in the soil moisture, and you're going to physically dig up a soil moisture sample from the depth that you're interested in. So you're going to have a certain amount of soil that you know the volume of, and then you're going to weigh that soil immediately after you take the sample. So now you know the total weight of soil and water within your sample. Then you take the soil back to your lab and you dry it. This evaporates any water that's in the soil. Then you're going to weigh your sample again. So now you have the weight of just the soil with no water in it. Now you can calculate the weight of water that was in your sample because you know the total weight before you dried it and the weight after you dried it. And because we know the density of water, we can convert that weight of water lost into a volume. And because you know the total volume of your sample, you can divide the volume of water lost divided by the total volume of your sample, and voila! You'll get a volumetric soil moisture content. You guys can probably tell that gravimetric soil sampling takes a lot of time. And there's an additional problem, in that you can't just take one sample. You have to take a lot of them. Because a gravimetric soil sample is only going to tell you the soil moisture for that little bit of dirt that you dug up, and soil moisture is pretty spatially heterogeneous, so you need a bunch of samples to get a good average for your area of interest. A slightly easier way to measure soil moisture is to actually use what's called a soil moisture probe. This is one example of a soil moisture probe, but there are a bunch of different brands. One thing that all soil moisture probes have in common are these little metal prongs here. And you stick these prongs completely into the soil, and they measure the dielectric constant, which itself is related to soil moisture. Wetter soils have higher dielectric constants and vice versa. These probes are cool because you can take many samples quickly or you can permanently or at least semi-permanently install them into the ground to get continuous monitoring of soil moisture. The bad side to these probes is that you actually want to calibrate them using soil from your region of interest in a lab first so that you can get the most accurate soil moisture readings. These probes also still only sample soil from a relatively small volume, so you do either need to take multiple samples or have multiple probes to get a better aerial average. The third and final category of soil moisture monitoring methods that I'm going to discuss today is satellite remote sensing. Are there other ways to measure soil moisture? Sure, but this is already getting too long. In recent years, there have been significant investments into satellite technologies to measure soil moisture. The two most recent ones are the European Space Agency's Soil Moisture and Ocean Salinity, or SMOS, satellite, and then NASA's Soil Moisture Active Passive, or SMAP satellite. Both of these are satellite radiometers, which measure the emissivity of the soil, which itself is related to soil moisture. Both of these also carry L-band antennas, which is part of the microwave spectrum. So now I think it would be a good time to talk about why we actually want to use GNSS-R to retrieve soil moisture. And one of the main reasons is actually the wavelength of the GPS signal itself, which is also L-band. L-band signals are used by other satellites that have been specifically designed to sense land surface hydrology. The wavelength is relatively long, around 19 centimeters, and in general, the longer the wavelength, the greater the ability of the signal to penetrate through dense vegetation canopies to actually see what's going on at the surface. L-band signals can even penetrate the surface a little bit, down to about 5 centimeters. So anytime we talk about soil moisture retrievals using GNSSR or any L-band signal, we're talking about the soil moisture for about the top 5 centimeters of soil. In truth, longer wavelengths that could penetrate even further down into the soil column, like P-band, would be awesome to have, because then you could potentially start understanding how the root zone soil moisture is evolving. And root zone soil moisture is important to know if you want to start monitoring things like agricultural drought. However, P-band signals are tricky because their transmission is severely restricted in a lot of places, and there are a couple other complications to using P-band as well. So this is why L-band signals are often touted as being the ideal wavelength for soil moisture remote sensing, even if you'd also really want to use a longer wavelength like P-band. Another reason to use GNSSR to retrieve soil moisture is something I'm sure you guys are all aware of, and that's money. GNSSR satellites don't need to transmit signals. They just receive them. So the satellites can be made smaller and more lightweight, which makes them cheaper to launch. NASA's one SMAP satellite cost almost $1 billion. $1 billion! That is so much money. Cygnus, on the other hand, got 8 satellites on orbit for what? $150 million? That's 15% of the cost for 8 times the satellites. There's a common argument that you might hear that says, okay, GNSSR satellites are cheaper, but there's no way they could be as good, right? Years ago, I heard someone say that SMAP is kind of like a golden Cadillac, and GNSSR satellites will be more like a fleet of Chevy Cruises. Personally, I don't think that was fair, because at that point, we hadn't seen what GNSSR data over land would look like. And who needs a Cadillac anyway? I think what we've seen so far is that this original assumption about the quality of GNSSR data over land was perhaps a bit pessimistic. Another reason why we want to use GNSSR satellites to retrieve soil moisture is related to money, but not money. Because the satellites are cheaper to launch, we can launch entire constellations of GNSSR satellites like Cygnus, which decreases the temporal repeat time of our observations. Why is improving temporal repeat time important? I mean, SMAP gives us data once every 3 days, and once every 2 days as we move closer to the poles. So who needs soil moisture data more often than that? I mean, aren't we getting a little greedy? As it turns out, a 2017 paper in Nature Geoscience looked at data coming from SMAP and determined that, on average, 3 days after a rain event, the surface soil layer will only retain about 14% of the precipitation that fell on that layer. But guys, that means that 86% of that water is no longer in the surface soil. Where did it go? And when did it go? Did it evaporate? Did it infiltrate further down into the soil? Did it affect subsequent rain events? When did the 86% disappear? Within the first hour? The first day? We don't know. This brings me to the concept of missing scales. We know a fair amount about soil moisture at the point locations where we just happen to have soil moisture probes. But with the exception of only a few places, I'm looking at you, Oklahoma, soil moisture probes are few and far between. On the other end of the spectrum, we have soil moisture everywhere every few days from SMAP or other soil moisture remote sensing satellites. But all of these satellites have huge spatial footprints, on the order of about 40 by 40 kilometers. So there's a need for global, or at least quasi-global, soil moisture data at intermediate scales between that of the point locations of soil moisture probes and then the huge spatial footprints of radiometers. Satellite radars, like NASA's upcoming NCAR mission, could provide this type of data, as it will have a spatial resolution on the order of 25 or 50 meters. But that cool spatial resolution comes at the cost of temporal resolution, as NCAR is only going to have a temporal repeat frequency of about once every 12 days. And I think this is where spaceborne GNSSR data can really start to fill in the gap. Because we can actually launch constellations of instruments, we could potentially get surface soil information either daily or even sub-daily. And although we're still figuring this out, it looks like the spatial footprint of GNSSR data is going to be a lot smaller than that from satellite radiometers. Okay. Should we actually start talking about how we can use GNSSR data to retrieve soil moisture? I mean, if you guys are still listening, hats off to you. If you guys do have a general background in GNSSR, and again, I'm kind of assuming that you do, you'll know that the GNSSR data, or at least the level 1 data, come in the form of delayed Doppler maps, or DDMs. So each DDM contains a ton of information, and for the most part, those of us who are looking at DDMs for land surface applications try to summarize the entire DDM into one observable, instead of this big, complicated three-dimensional thing. There's been quite a bit of work done looking at how we can take the peak value of each DDM and relate that to an estimate of surface reflectivity, which itself should vary according to soil moisture. To do that, we use the bistatic radar equation. And the bistatic radar equation relates the signal that we actually receive to several variables. Some of them are things like the receiver antenna gain, the transmitted power of the GPS satellite, the bistatic range, and then also the surface reflectivity. Note that this denominator here adds the two ranges together and then squares them. And this actually assumes what's called a coherent surface reflection. And I'll touch on this a little bit more later, but just know that there are some people who would actually prefer for these two ranges to be squared and then multiplied together. But for what I'm going to talk about today, that doesn't really matter. Anyway, you can actually solve for surface reflectivity using the peak value of the DDM and then ancillary information pertaining to the antenna gains and ranges and transmit powers. And then surface reflectivity itself is going to be a function of the dielectric constant of the surface, the small-scale surface roughness, and the incidence angle of the incoming signal. So if you either have all of these variables or can estimate them, then you can eventually see how we could solve for soil moisture. So this is fundamentally why we think and why we know the DDM should be affected by surface soil moisture. In practice though, this equation doesn't really account for everything that we know will be affecting the reflected GPS signal. For example, large-scale changes in topography are going to cause this additional weird scattering of the signal that we haven't really been able to properly account for yet. And then of course, overlying vegetation will also affect the surface reflectivity, and the bistatic radar equation here, as I've shown it, also doesn't account for that. So it's not quite as simple as just popping in our receiver antenna gain, transmit power, bistatic ranges, and incidence angles, and then out pops soil moisture. So now maybe let's move on to the different options that are out there for actually using GNSSR data to retrieve soil moisture. This is by no means an exhaustive list, but I would say that these are the main approaches that have been tried so far. The first option, which is the one I'm most familiar with, is taking observations of surface reflectivity and then coming up with empirical or semi-empirical relationships between the observations of surface reflectivity and then an independent soil moisture data set. The soil moisture data set could be derived from other remote sensing data, like that from SMAP, or it could be derived from actual in situ observations of soil moisture from soil moisture probes. There have been quite a few people who have come up with linear regressions between observations of Cygnus surface reflectivity and then SMAP soil moisture, and I'm one of those people. I'd say that all of these efforts have kind of been variations on a theme, and the major differences between all of these efforts have been mostly in regards to how the data are gridded or subsetted or binned. Some of these groups also try to account for vegetation effects by including some sort of ancillary vegetation data into their retrieval algorithm. And I would say that all of these efforts have had at least moderate success. One of the most obvious drawbacks to this approach is that the ultimate soil moisture retrievals that were derived from the GNSSR data can only be as good as the soil moisture data that they were regressed against. So, for example, if you were regressing your reflectivity observations against SMAP, and then SMAP has a lot of error in a particular region, then your soil moisture retrievals will also have that error. I think this approach is cool because it's a relatively quick way to explore the potential of Cygnus or other GNSSR satellites to retrieve soil moisture, but I wouldn't say that this approach is able to really push the limits of what GNSSR data could potentially do, because you're always going to be constrained by your training data and the limits on those empirical relationships. Another option that some groups are trying is to actually come up with a physical model to understand how soil moisture should affect the reflected GPS signal, along with considerations for things like vegetation parameters and small-scale surface roughness. So in this case, you don't need an independent soil moisture data set to regress your data to or calibrate it with, which is great because I think with this approach you can really start exploring just how good GNSSR data truly can be relative to other sensors. But on the other hand, this approach really requires high fidelity, appropriate, really good ancillary information of vegetation, small-scale surface roughness, and other factors, which is hard to find. I'll touch more on that later. And then the third option I've seen is people using machine learning to come up with soil moisture retrieval algorithms from GNSSR data. And I guess this really falls under the empirical or semi-empirical category because you still need a training soil moisture data set, but in this case you're letting the machine do the regressions instead of doing them yourself. So there are some tricky things about using GNSSR data, lots of tricky things. And this extends to land surface applications beyond just soil moisture. The first one is the non-repeating nature of the observations themselves. GNSSR data are collected somewhat randomly over the surface, the point locations of which are determined by both the locations of the GPS transmitters and then the GNSSR receivers. And these positions are constantly changing. So we'll often see an observation at a particular location on one day, and then the next day there will be an observation close by, but not at that exact same location. This makes gridding the data interesting, and so far everybody seems to be doing it in a different way. Though, let's be honest, if gridding is one of our biggest problems, then I think we're doing okay. There's also this pesky problem that, we don't actually control the GPS satellites, and the military can either turn up or down the transmitted power whenever it wants to, and then not tell us. A higher transmitted power will cause a stronger surface reflection. So if you don't know that the transmitted power was turned up, you're going to see a stronger surface reflection, and you might accidentally think that stronger reflection is due to maybe an increase in soil moisture, when in fact it was just a change in the transmit power. So you'll probably want to be able to monitor the transmitted GPS power, maybe by using an upward-looking antenna. There are several things we also don't yet know about the GPS reflected signal. For one, we haven't decided under what conditions the reflected GPS signal will be mostly coherent and under what conditions it'll be mostly incoherent. Sure, in theory we can say, once the RMS surface height exceeds 5 centimeters, then the signal will be mostly incoherent. Okay, that's fine, but how do we measure the RMS height of the surface everywhere? We can't. Digital elevation models are too coarse and they have too much relative error to be able to actually adequately describe the RMS height of the surface. Even LiDAR data with 5 to 10 centimeter accuracy just isn't quite good enough to get at those small scale changes in surface roughness that we need. Whether or not the signal is coherent actually really does matter. Not only will it change how we correct our surface reflectivity for things like bistatic range, but it also determines how big our spatial footprint is. A coherent reflection will have a pretty small footprint, maybe about a half kilometer, but an incoherent reflection will have a big footprint, maybe on the order of 25 kilometers. That's a big difference, and it's something that we don't have a good handle on yet. And then there's the sensitivity to things other than just soil moisture. Like all radar data, we are also going to be sensitive to things like small-scale surface roughness, like vegetation, like large-scale changes in topography. How sensitive, you ask? We don't know. We're still trying to figure that out. In my opinion, one of the best ways to start figuring some of this stuff out is to actually have more aircraft data. Teasing out the intricacies of the surface from space is really hard, and it would be nice to have repeat flights over a certain region or regions that are well instrumented. One of the last things I want to do is mention some of the common pitfalls I would avoid if you want to start taking your own GNSSR data and seeing if you can also retrieve soil moisture from it. The first thing you'll be tempted to do once you've collected a bunch of GNSSR observations is to match them up with coincident soil moisture data, either from SMAP or SMOS, and then you'll make a big scatter plot of the data. And trust me, if you do this, you will fail. Making general global scatter plots is only going to result in this big, noisy cloud of data with no discernible trend. And this will make you depressed because you'll think that your data aren't sensitive to soil moisture. Even trying to bend your observations by, say, a vegetation metric like NDVI is still going to leave you with a ton of noise. Slightly less noise than in the first case, but it's still not going to look very good. And the problem, I think, is that we still don't know how to properly account for these complicating factors like vegetation. So I think our first instinct is to just throw some easier, well-known ancillary data set into the mix to try to see what pops out. But if the ancillary data set that you're throwing at the problem isn't actually a good descriptor of what's going on, all you're going to do is confuse yourself even more. For example, NDVI is a really common metric that's used by a lot of people to describe vegetation, and I think it's useful for a lot of things. But NDVI is just a measure of how green the vegetation is. That's it. Do you think GPS reflections care at all about how green the vegetation is? Not really. The reflected GPS signal is responding to a bunch of different vegetation components. One of the main ones is probably the water content of the vegetation. And it's well known that vegetation greenness is not always a great indicator for how much water is in the vegetation. So if you just throw NDVI at your GNSSR problem, you'll probably be accounting for vegetation effects in some areas, but actually making it worse in others. So I would just advise you guys to really think about the ancillary data sets that you're using before you incorporate them into your retrieval algorithms. Finally, and I can't emphasize this enough, account for surface water. If you want to look at GNSSR data and its sensitivity to soil moisture, but you don't remove your GNSSR observations that are affected by surface water, you're in for a world of hurt. I can't think of anything that GNSSR observations are more sensitive to than surface water. And this huge sensitivity is really going to hide any soil moisture signal that you're sniffing around for. Okay, so I think I've talked at you guys long enough. I hope you learned something about soil moisture today. And if you think I've left anything out or have any further questions, then feel free to email me. So that's all for now. See you next time.
Thank you very much. Thanks for Dr. Chew, Clara's great talk. And I think we still have time for quick questions. Anyone want to ask questions now? Actually, although I'm not a soil moisture person, but I would like to ask a quick question, but maybe a little bit trivial. So for the GNSSR, for the footprint, that if this footprint is sort of a mix of different type of vegetation cover, and for that, for this kind of situation, do you need to consider the fraction or the contribution, or how to take care of this? Thank you.
Yeah, I think in an ideal world, you would want to account for that. I don't think I've seen anyone actually do that yet. But the sensors like SMAP and SMOS, they do have approaches for trying to handle mixed pixels. So yeah, I think if you did want to come up with your own soil moisture retrieval algorithm, it would be great to take into account mixed pixels like that, but I don't think we're quite that advanced.
And also, I believe there's a strong diurnal variation in the soil moisture. So far, can the GNSSR data capture this kind of variation?
In theory, yes. I don't know. I've heard some murmurs about people maybe trying to look at that with the Cygnus data. I haven't seen any results. Another thing to take into account with the diurnal variations in soil moisture would also be the diurnal changes in vegetation water content. So I imagine those two kind of signals in the GNSSR data would be mixed, and you'd have to untangle them somehow.
Okay, thank you very much. Today, we are very thankful for all speakers and for the great presentation. And we just started our satellite mission for the Triton, the GNSS-R. And we are hoping that there will be more for this satellite in the future. So we are hoping we can keep learning from you guys and wish to catch up and with the progress like all you have. Thank you very much. So I would like to close today's session. Thank you.